Hydra, in addition to that, incorporates some protection mechanisms. So not only is there the function cosine of x, but there's who can call cosine of x. Those kinds of things, all right? Then, so if you drop down then to the next paragraph, he says a procedure object contains a list of references to other objects which must be accessed during the execution of the procedure's code. All right, so if I'm in a certain procedure and I need to, in effect, call some other procedure, because of this protection mechanism, I have to have the privileges that allow me to go out and do that with this other procedure. So that you've got this hierarchy of not just codes, but this hierarchy of privileges, if you will. All right? Good. And so he says it therefore defines not only which objects the procedure may reference, but also what actions it may perform on these objects. All right? The terminology we use is a capability-based operating system. Capability-based. All right? So the idea of access control lists, kind of like what Microsoft Windows NT. Okay, access control lists, et cetera, et cetera. It's different than the simple protection bits in a Unix operating system. All right. By the way, if it's more complex, what can you speculate about the running time, the execution speed? Okay, if I got to wade through more crap to decide if you can do what you want to do, well, it's possible that it'll take longer. Okay, so you trade performance for capability for features. Standard story. All right, good. So then, going up, next column, he says, a procedure is a static entity, okay, whereas a local namespace, what he calls LNS, is the record of the execution environment of a procedure when that procedure is called. So they're sort of similar. So the procedure is the, sort of the code itself and all of the things that it needs to call and all the protections and all that. And when it's actually in execution, that's called an LNS, a local namespace. It's a subtle distinction. All right, good. So then, moving down, in the next paragraph he says, we've been basically using capability loosely. And he goes down and tries to tie down precisely what he means by capability. He says this: a capability consists of a reference to an object together with a collection of access rights to that object. Okay? And so then, possession of a capability is the evidence that the processor may access the object in the ways, by the way, and only the ways that the capability allows. All right? And so the next thing he points out is that these capabilities are manipulated only by the kernel. Okay, so this is a sort of something that only the operating system kernel can do, and that's how they avoid, spoofing and all these other things. Okay, because the user himself can't modify capabilities. Only the kernel. All right, good. So moving on. Okay. Go to the very bottom of the page 339. He says, let's review the major actions of the call. This mechanism he calls call. Okay? So, an executing body of code first notifies the kernel that it wishes to call a procedure. All right? The kernel then does what? It examines the parameters, specifically the capabilities, the parameter capabilities supplied by the caller, and has to do what? Are you allowed to do this? So it goes through all of the intrinsic protection. Okay? If so, the kernel creates a new LNS, local namespace. I'm going to call cosine of x. I tell the kernel, I want to call cosine of x. Okay? The kernel knows about this procedure, this piece of code called cosine of x, and it says, okay, are you allowed to call cosine of x? What are you allowed to do with cosine of x? And if everything's hunky-dory, then it takes cosine of x, puts it into an execution environment called a local namespace, and it begins to run. That's the idea. All right? The callers, so the kernel creates a new LNS, which defines the new environment. The caller's LNS is superseded by this new LNS for the duration of the called procedure's execution. We would call this a blocking call. So if I call cosine x, whatever I was doing stops until cosine x gets done and comes back. We'll see that later operating systems allowed what they call non-blocking calls, where I can call it, and while it's doing its thing, I'm continuing to do mine. All right? So, but in this case, it's a blocking call. All right? So, good. The body of code associated with the callee receives control from the kernel and begins executing. So cosine x fires up and does its thing. When it finishes, it returns by way of the kernel. It goes back to the kernel and goes, I'm done. And then the kernel deletes the local namespace and goes back to the previous environment, and mama runs again. All right, good. So
that's the capability, basically.
Well, the capability piece, yes. Capability piece is the checking of whether or not I can call cosine.
Okay.
And other things. I mean, the capabilities might be read capability, write capability, execute capability.
Right. Okay. All right.
We'll see later on a specific example of that. Maurice.
So what if you can't?
Then it won't happen.
So there's no type of security?
Well, that is the security. Sorry, you can't do that. I imagine in a real implementation, you'd get some message that says, you're an idiot, you can't do that. Okay? Or surely you jest, or something like that. Okay? So here we go. Moving on then. All right? Moving down about half a paragraph, it says, they're now going to talk about this thing called a process. All right? And he mentioned this is kind of our intuitive notion of a process. All right? And so in some sense, it's the smallest entity which can be independently scheduled for execution. All right? And so what he's really saying is that this process is some set or stack of LNSs which represent the cumulative state of a single sequential task. So I call cosine, and maybe the way I implement cosine is by calling sine and doing some manipulation with the angle. So there'd be my code plus the cosine code plus the sine code. Those three LNSs would collectively be the process. That's the idea. All right? Good. Here we go. Let's see. Hydra implements inter-process communication and synchronization. How? This is interesting. By providing elementary message buffering primitives and Dijkstra-style semaphore operations. So here was Dijkstra and Brinch Hansen going, no, my way is better. No, do it my way. Your way's broken. And this guy goes, you know what? There are times when you need both. Okay, sometimes message passing makes sense. Sometimes semaphores make sense. Okay, so that's the way it is in a modern operating system. You use both.
We had to explain semaphores in homework.
Yes. And so semaphores are one of the primary synchronization primitives that allow for inter-process communication to take place. Okay? And the other way is through message passing.
That's the send message, wait message.
Okay.
So does it allow the parallel process to go through that?
It prevents, so synchronization prevents race conditions from taking place. Do you remember I did the
Round robin thing?
No. Do you remember that I did the illustration with my wife and I at the ATM?
Yeah.
Let me do it again real quick just to make it clear. Here's some central bank, okay, with its computer, okay. Here's the ATM, which is what?
ATM.
A computer.
Yeah.
All right. And here's the other ATM, which is what?
A computer.
A computer. Right. So I got three computers connected in a network. What's that called?
A cluster.
It's called a cluster. Okay. So here I got the cluster. All right. So I've got some balance down here. All right. Balance equals $1,000. Okay. I'm going to put money in. I'm going to put $100 in, and Lisa is going to take out $10. If you don't do it the right way, you can end up in trouble. All right? But we both read the balance. Bam. So now I've got over here a copy of balance, which is 1,000. And Lisa's got a copy of balance, which is 1,000, right?
Mm-hmm.
So she pulls out the 10, right? Updates her local copy. Now it becomes what?
9,990.
All right? And then she updates
990.
it. Bam. It goes back, right? Well, let's say the other thing happened. That would be actually to my advantage. Because I would then take, so she takes the 990, writes it back, and now the central bank thinks that the balance is what?
990.
990. But in the meantime, I take the balance of 1,000, add the $100 to it, so what do I think I now have? $1,100, right? And it goes back in here, now the balance is $1,100. Okay, so do you see that?
Mm-hmm.
Okay, that's different. Now what if it was the other way? What if I got there first? So I put my balance plus 100 is 1,100, and I put my 1,100 in there, okay? And then Lisa takes her balance, which is 100,000, minus the 10 is 990, and she puts it back. So do you see that the resulting state depends upon the order of execution?
Yes.
That's called a race condition, all right? And so to avoid these race conditions, you use some type of a synchronization mechanism.
The real-time clock?
Okay, no, synchronization is when it serializes the behavior.
Okay.
Okay, it causes a proper serialization of the execution, so that no matter what order takes place, the result is the same. Okay, if this were done with semaphores, then what would happen is this. Whichever one of us happened to get there first, we would hit our P. Okay, so good. Say I did it first. I hit my P, and I go into the critical section. What's going to happen to Lisa?
She's going to have to wait until...
She's going to go on the waiting list. So she doesn't get the balance of 1,000 yet. She's on a waiting list.
Right.
Okay, I quickly do my transaction and put back here what? 1,100, right?
Mm-hmm.
All right. Then I do my V. And when my V takes place, what happens to Lisa?
She's on the waiting.
She comes off the waiting list and she grabs the balance, which is
Oh,
1,100.
Right.
Right?
Right.
Pulls the $10 out. Now what is it? It's
1,090.
and it goes back, and I get 1090, which is the right answer. You see it?
Yes.
All right. Now, if it's message passing, okay, it's the same kind of a deal.
Yeah.
All right. Instead of having these P's and V's, it's done with messages.
Right.
It's done with messages. I send messages to allow for the synchronization. Okay. I might say, hey, I need the balance. Is anybody else looking for a balance? No, they're not. Okay, here's the balance, 1,000. All right? Now I'm allowed to do my thing. All right? In the meantime, Lisa comes down and goes, hey, I need the balance. Is anybody else using it right now? And the main computer goes, yeah, someone else is using it. And hold on, I'll get it to you momentarily. All right? And so as soon as I get done, I go, here's my new balance. As soon as he updates it, then he goes back to this one, goes, here's the balance that you wanted. So it's done with message passing instead of a shared memory P and V operation.
Now, in none of the cases are these two processes going to communicate to each other directly, right?
You could have. That's a possibility as well. So you could eliminate the middleman. Sure, that's a possibility. I don't know how it's actually done. Okay, I was just trying to concoct an example of how these inter-process communication has to take place and how it has to be synchronized through either message passing or through semaphores.
But we can't have an operating system who would let that happen, right?
Well, you could, but it would be broken. No, maybe I misunderstood the question.
We can have an operating system which can facilitate the processes to communicate like that.
That's one of the features that an operating system, a multi-programming operating system has to provide, is either synchronization through message passing, inter-process communication synchronization through message passing, or IPC through semaphores, or something else.
Yeah.
So it's a critical requirement of any multiprocessing system, or you're going to get race conditions,
Yeah.
which is bad mojo. Okay, race conditions are bad mojo. All right. So then, good. Moving on.
I got a question.
Glasses are falling apart. Old man has to wear his glasses on a string. All you whippersnappers.
Who you talking to them?
All you gotta do is tell Lisa.
Good. So moving on then. We now talk about the protection mechanism. He makes this distinction. He says, protection is a mechanism, whereas security is a policy. All right? Security is a policy. Okay? Good. And what I found really interesting about this paper is they have completely dispensed with the idea of ownership. There's no such thing as ownership. We think in Unix, well, I'm the owner of the file, and I can give you read permission, I can give you write permission, but ooh, it's still mine.
Right.
Okay? That does not exist in Hydra. There's no idea, there's no notion of ownership. There's simply capability. What can you do? All right? So then he goes on, he says, the obvious candidate for the unit of protection is the object. All right? Good. So, excellent. Good. So, Hydra provides a protection mechanism for the application of procedures to instances of resources. All right, good. So here we go. And then some technical detail. Okay. Then, on the next page, 341, it says, each capability, okay, and remember, that's a capability is essentially a reference to an object. That's what a capability is. It's a reference to an object. Okay? And implicit in all of that is what I'm allowed to do, include not even see that object. So a reference to the object is a capability. Good. And so he says each capability includes information detailing the operations which may be performed on the object referenced by the capability. All right? Good. And so what happens? The kernel examines the rights list and prevents the operation when a protection failure occurs. So this is the, what are you, an idiot message, right? Surely you jest, right? That should be the only error message. Surely you jest. That way we get rid of all the riffraff trying to take over our domain. You shouldn't be stupid. If you don't know how it works, you shouldn't do it. Just kidding. Okay. Good. Good. I did point out, he talks about this idea of a directory structure. He says that many variations are possible, and it turns out that the nature of what he calls a directory subsystem, because of the extensibility of Hydra, is completely up to the user. It's completely up to the user. All right? Good. So then he gives this example. This is a bibliography application. All right? Notice, okay, so he's got so this is on the bottom right of page 343. So there's the update. So these are the things that you can do. You can update. You can print. You can print without annotations. And you can erase. All right? So those are the things. These are the operations